Hi, I'm Geoffrey Fox, and I'm going to tell you about the Department of Intelligent Systems Engineering at the School of Informatics and Computing at Indiana University, Bloomington. This new department has 19 faculty, 56 undergraduates, and 43 PhD students. It will be starting a master's program in the near future. First, we better decide what intelligent systems engineering is. And ingeniously, the name can be parsed in two ways: intelligent systems engineering or intelligent systems engineering. And so as in systems engineering, that's the design of large systems, and so we certainly include that. But with the intelligent systems side, we're actually incorporating computing and artificial intelligence into the design of these systems, because intelligent systems imply the ability to sense the environment and act accordingly, and they involve things like machine learning and artificial intelligence, devices on the edge, and cloud computing at the back end. So more precisely, when people ask me what intelligent systems engineering is doing, it is studying the whole system, from the raw building the system, acquiring the data, signal processing, and then the final filtering and understanding to get wisdom and ability to make decisions. Of course, this is a totally new program. And in setting up this new program, we've tried to build in the state of engineering today. So we tend to be focusing on rather different issues from other engineering departments. The example I usually give is a car. If you want to build a traditional car with giant factories, then you don't come to our department. If you want to design the autopilots and autonomous technology to allow it to be the car of the future, then that's what we will do here. This chart here, which has been with us from the beginning of the program, describes the essential idea. We have 6 majors: computer engineering, cyber-physical systems, environmental engineering, molecular and nanoscale engineering, neuroengineering, and bioengineering. And they are linked together by a set of common ideas. At the middle of these ideas is intelligent systems, but it also has big data, high-performance computing, modeling and simulation, design of the user interface, as well as the design of the whole system, traditional engineering, signal processing, control theory, information theory, and then all of the cyber-physical systems, sensors, detectors, instrumentations, robots, Internet of Things, and from the small to the large, the computing hardware that enables all of this. So that's what we say. We go from the small to the large, from the edge computing, which is driving a lot of the commercial activities today, because almost all the data comes from the edge, whether you're a person tweeting away or as I say, a smart car. You're at the edge, but your data actually goes to the middle, to the either the cloud, and clouds today are actually capturing all the ideas of high-performance computing. So the cloud of the future will be high-performance systems. And they, of course, are notoriously big. They're giant systems occupying football fields worth of area. And they're the ones that are doing the big data computations of today. And all our students have courses on edge computing, cloud computing, high-performance computing, machine learning / artificial intelligence, and the modeling of simulation, so you can understand before you use it what your system will do. So let me just spend a little 2 or 3 slides on this concept of intelligent systems, because it's sort of, it's not the dominant feature of our program, but it's sufficiently new it deserves a little bit of attention. So here I've given 9 headlines from 2017, the last 6 months, and they all have the word artificial intelligence or machine learning in the title. They all have giant companies which are sort of engineering companies. Google has computer engineers, and Tesla is building cars, and Intel is building hardware, as says Apple. And these engineering companies all effectively say that they are AI companies, and that success in AI is critical to their future. The only person who might be a slight outsider there is Elon Musk from Tesla, because he's worrying that AI will actually get out of control and take over the world. But these remarks here point out how essential it is for a modern engineer to understand artificial intelligence and machine learning. And in articles on these titles, it is noted that these companies, which are becoming AI companies or AI first companies or machine learning first companies, they need employees. And we're one of the few engineering programs that builds in AI into our curriculum. If you go to a well-known job site, Indeed.com, and look for trends, you can see from the top that I've done a few trending here. Big data engineer. Data scientist, that's not engineering, but it's sort of related to what we do. That's one little bit down. Then becomes machine learning engineer. All of these are above computer science, and there's not so much for artificial intelligence engineer. People tend to advertise for the technology needed machine learning engineer. It's actually worth noticing, although there's obviously a lot of interest, all of these job categories are around 0.3 to 0.5% of the total jobs posted on Indeed.com, that actually the largest of the ones we care about is computer engineering, which is about 10 times that in size at 4.5%. So our program is clearly addressing jobs which are very much in demand today. So now let's get down to a little bit more detail. We have actually 7 tracks. There are 6 I've already mentioned, starting with computer engineering. But I added here the sort of base track, which means you just don't specialize in anything, which means you do intelligent systems. If you're an undergraduate, or in fact a graduate student, we have 4 offerings, 4 tracks: computer engineering, cyber-physical systems, which are pretty close. They only differ in the last few courses. Bioengineering and nanoengineering, those are the 4 undergraduate tracks, also say graduate tracks. And then we have the 3 graduate-only tracks, which are available on master's and PhD: environmental engineering, neuroengineering, and intelligent systems. So we saw in the previous slide that computer engineering is actually the core degree, with 4% of the jobs in Indeed.com wanting that knowledge. And it covers essentially all aspects of our program. It relates to hardware at the edge, hardware in the middle, or in the center, large scale. It involves software, it involves algorithms. And you can become a big data engineer or a deep learning engineer, or you can be an engineer building the hardware for the devices that are going to monitor the progress of today's autonomous vehicles. And you can focus on the manufacturing, where digital manufacturing is very important, and of course digital finance is very important today. The finance companies, they hire lots and lots of people from this area. Cyber-physical systems, as we pointed out, is closely related to computer engineering, because it's the computer engineers that builds the actual systems. But in a CPS focus, you'll learn about robotics. You'll learn about the Internet of Things. You'll learn about smart homes and smart cities and so on. And all of this is critical for intelligence. There's a lot of hype just last few days about Amazon Alexa being very popular with their new Echo devices. And that's all AI in the home. I went to the Consumer Electronics Show in January in Las Vegas, and it was full of startups from machine learning faculty who are building cuddly teddy bears who were able to use that deep learning in the cloud to answer your nifty questions. The last two undergraduate degrees are bioengineering and nanoengineering, and both of these build on strengths that are already at Bloomington in the life sciences, the computing area, and also just basic engineering practices. And they span biology, medicine, environmental remediation like toxicity and so on. You can have careers in medical devices. We have special interest in wearables, the actual hardware and analysis of data from wearables, developing drugs, engineering tissues, building real new tissues which can be used in transplants, environmental engineering, and both at the technical and the policy level. And of course, you can either get jobs in industry or jobs in academia. Nanoengineering spans everything from electrical engineering to material science. And you're going to be building, because it says nano, you're going to be building these cyber-physical systems because those are small. And that's what nanoengineering tells you how to do. If we look at our two initial faculty, one is building kilometer-sized fiber networks, which are intrinsically electronically sensitive. Another is looking at the properties of the nanomaterials, doing large-scale simulations. All of these are part of a nanoengineering degree. Namely, and you will say you will either can do experimental or computational and somewhat the theoretical, because only the people who understand what's going on will actually know what to do. So everything we want to do is built around these basic philosophies of doing and learning by doing, applying what you learn, and looking properly at the overall context and generalizing it. And so we have lots of labs. We're using, actually today, we're using our labs to offer summer camps to high school and middle school students. And we're trying to show how engineering applies the principles of science to create things of importance and interest. And as we've stressed many times, everything requires a fundamental understanding of computing. You can't do machine learning without computers that are optimized to do that. And in fact, a lot of progress has been made these days in such computers. And examples of work we do is that on understanding images like pathology images or remote sensing images, and looking at the nanosensors. I pointed out these faculty building the large-scale fiber systems. Those can be cut up and made nifty clothing, which you will have a totally active dress to monitor your life. So computing has begun very early in the program, and it's required for all students. If we look and now come to the undergraduate degree, Indiana University Bloomington only has 120 credits. Other universities have more, especially for engineering. In our engineering degree, it's a technically sophisticated degree at the level of any other engineering program in the nation. We have 69 credits go to engineering, 21 to general education, and 30 to math and science, and there's 6 electives in those engineering credits. So if you look at the engineering degree itself, the credits itself, there are 30 credits which are taken by everybody, whatever your track, bio, nano, CPS, computing. Then after that, if you're doing CE and CPS, there are 15 credits in common between those two tracks, the so-called CE/CPS core. And then you have an 18 credit specialization track, for instance, which you would decide you might do specialized cloud computing for computer engineering and specialized robotics for cyber-physical systems. Bio and nano differs first in semester 4, the second semester of the second year is actually identical to CE and CPS for the first 3 semesters. So you don't have to make up your mind to the last minute. And it needs an advanced chemistry course, which is taken by all bio and nano students. After that, there are a total of 33 credits divided into cores, which are sort of required for nano and bio. They're separately They're not like CE and CPS where it's in common. These are actually separate. And then they're again like CE and CPS, specialized tracks of 18 credits where you choose from a variety of courses. Well, this is getting pretty complicated. Just to dazzle you with numbers and letters to show that everything here is for real. This shows you a 4-year degree map. Each of those rounded rectangles is a semester, and there are 8 semesters, starting at the top with semester 1 and ending at the bottom with semester 8. And inside each of those containers are the courses you take that semester. And if you look at it, you can see in detail that there are different colors. The yellow colors come from the university. The red colors are this common 30 credit core, which I mentioned. I should note that not all of these courses are 3 credits, some are smaller than that. And then after that, we have the blue here, which is the common CE/CPS core. Note that Intelligent Systems 1 is taken by every student, whether you're Bio, Nano, CE, or CPS. Intelligent Systems 2, that's appropriate for CE and CPS students. Then, of course, you always take statistics and math and physics and chemistry. In the last 2 semesters, there is a project capstone, which is typical of any engineering program, which you need to take to pass the curriculum. But these courses here, the dark brownish ones are the track, the computer engineering track, and this is just a particular selection, like the deep learning, the operating systems, high performance computing. You'll choose from a large number of courses to get those. Here's the same thing for CPS. By definition, it only differs in the dark brown courses because everything else is identical between CE and CPS. The red, the yellow, the blue are the same. And it's just here, for instance, we've given the CPS student has been able to take Robotics 1 and Robotics 2, Advanced Cyber-Physical Systems, and the Internet of Things, a wide variety of cyber-physical system courses. So here's some comments on sort of overall issues which people ask about. Well, we know we want to be ABET accredited, both at the undergraduate and master's level, and we've designed to meet those requirements. Unfortunately, you're just not allowed to ask to be accredited until your first students have graduated, and that will be 2020. By that time, we should have masters and undergraduates who've graduated, and we can go up for ABET accreditation. We believe that we will straightforwardly meet the ABET requirements because we've studied what's necessary to do, and we're carefully documenting our processes so that we'll be able to do that. And we will seek retroactive accreditation to all the students who've graduated before the accreditation is granted. Already it's a degree from Indiana University, so it is accredited, it's just not accredited by ABET. We have good scholarships, both for PhDs and undergraduates, and there are also other things we can fund. There are summer camps, which I mentioned. There's summer research and academic research available for the undergraduates in our program. You just need to ask. Now we have a few slides about our 19 faculty. At the top we have our dean, the most important, who is in computer engineering and intelligent systems, and that's Raj Acharya. Below that is me. I'm meant to be chair, so that's why I put myself there. I do cyber-physical systems and intelligent systems. Martin Swaney is my colleague, associate chair. He has similar interests, but with a greater focus on computer engineering and embedded systems. We round off this page with Kadi Bana, who is a distinguished professor, and which is the highest honor you can get at Indiana University. And she builds intelligent systems and focuses on data analysis and visualization, particularly in studying science, trying to visualize scientific progress and achievement. Now we have another 4 senior faculty. These are all tenured. James Glazier leads this is the most senior bioengineering faculty. He works on so-called biocomplexity, toxicity, virtual tissues. Judy Chu is in the computer engineering and intelligence systems. She teaches the cloud courses and does parallel computing, big data, and her students get very good jobs. Thomas Sterling, as in fact the students of all our faculty, I should say. Thomas Sterling, a very distinguished engineer, MIT degree in electrical engineering. He works on extreme scale, high performance hardware and software. Finally, we have a new tenured faculty, Clint Whaley, coming to us from Louisiana State University, and he is in also high performance computing, but he has tremendous expertise and renown in the area of performance engineering, how to get the best performance out of your software. Now we come to the more junior faculty. These are the ones that joined the first semester of this year, fall of 2016. Li Jiang comes from AMD, where he was a computer engineer. He does high performance computing hardware studies, comes from Pittsburgh with a PhD. Minji comes from the University of Illinois at Urbana-Champaign, Minji Kim. He is in intelligence systems and studies signal processing and machine learning for multimedia applications. His course in that area is very popular. Vikram Jadeo is also from UIUC, but as a PhD. His postdoc was at Johns Hopkins and Northwestern, and he is using high-performance computing to do large-scale simulations of material science. The other nanoengineering faculty I mentioned is Alexander Gumenik, comes from Hebrew University, MIT, and a lead engineer in a 3D printing startup called Formlabs, which actually is builds very popular 3D printers. And he is the one whose lab is going to be building scalable, electronically sensitive, which is what it means by intelligent fibers, using an ingenious combination of fiber technology and 3D printing. The other three faculty joining us this year, Elif, who is in neuroengineering. He is building software called DiPi to study large-scale imaging, especially that for MRIs. And he has a PhD in brain sciences, a good subject, from Cambridge University. I come from Cambridge University originally. Maria Bonderson-Bolin is in a bioengineering experimental. She does experiments on zebrafish to understand their reaction to various environmental effects. Paul Macklin is more computational, though he also does data analysis, and he is studying cancer and has a lot of actually good funded projects in those areas. Now we come to the faculty joining us in August 1. First of this is Lentao Lu, comes to us from the Distinguished Robotics Laboratories at University of Southern California and Carnegie Mellon. And he works in the area of autonomous robots, planning, studying the planning and decision making with a special application to environmental studies. These robots typically are marine robots. Etai Roth comes to us from Seattle with a PhD in mechanical engineering, so he is actually going to play a key role in the mechanics part of our robot courses. But his research involves the study of these differences and similarities between animal and robot flights. He studies moths and robots and that way they fly. Greg Lewis comes to us from the University of North Carolina, Chapel Hill, and the University of Illinois at Chicago. And his expertise is wearables and cyber-physical systems. So he's a bioengineer. He works with the Kinsey Institute, which is really famous at IU Bloomington. And he will have his home. His lab will be in Kinsey, but his home and his students will be in engineering. Feng Gu is the final one of our 19 faculty, and he will also join us August 1, and he comes from the bio-nano intersection. He uses so-called acoustic tweezers to capture localized effects and use that to build biomedical devices. which can be used to analyze single cells, do various diagnoses in neuroscience and virology. He is currently a postdoc in Stanford. Let's now just have a quick discussion of the PhD program. We have those 7 tracks I mentioned. We have a pretty healthy PhD program, 43 students in this fall. And if you look at how they're divided, 22 are computer engineering, 8 cyber-physical systems, 3 are in intelligence systems, the study of the machine learning and big data issues, 5 in bio, 1 in nano. I should say nano actually has more students, but they actually are enrolled in other tracks formally, but I suspect they might move to nano. 3 in neuro and 1 environmental. I should say our environmental work is in the collaboration with SPEAR, which is a famous school at Indiana University Bloomington with a focus on environmental issues. The degree, as all degrees at IU Bloomington, has 90 credits, 9 of which must, again by Bloomington rules, be a minor, which can be inside or outside in the engineering department. They're required to be 24 credits for the engineering major, of which 6 of them are introductory courses, 1 introduction to the whole concept of intelligent systems engineering, and 1 course which is specific to one of those 7 tracks. Then you have 9 specialized credits in your major and 9 other engineering credits. And there you have to pass a qualifying exam customized by the committee. That we always give you a committee, and that could, for instance, it can be specialized by the committee, but typically would require at least writing a top quality professional paper and an oral exam. Our master's program is fully defined and actually approved by the university, but not approved yet by the state. We hope to offer it the spring of 2018. It is 30 credits like many master's programs and has 2 modes, traditional, usually takes a couple of years or at least 1.5 years, and it can be, but it also can be accelerated, which is sort of a traditional shared bachelor's and master's degree taking 5 years, where you share 12 credits between the bachelor's and master's program. There are 4 paradigms you can take the master's degree: pure coursework, an internship-oriented one, a project-oriented one, and a research-oriented one. The latter is explicitly aimed at those students who view the master's as a stepping stone to the PhD. To satisfy the paradigm of internship, project, and research, we're going to take 6 to 9 credits of specialized courses. As well as that, all students have to take 15 credits of graduate level in engineering courses. Of those courses, there will be the general core, which is this E500 to 507 set of introductory courses, a computing core and math core. You're likely to place out of those, and a core for each track. The core tracks are just 2 courses each. Well, after you've done all of this, then you just make up the 30 credits for the electives. And that's the end of this discussion. Here are some students assembling embedded systems. And I wish everybody the best of luck, whether they're faculty or students or just looking on in wonder. Thank you very much.